right, today we are, sorry, I just realized this slideshow automatically progressed these forward. There we are. So today we are in session 2 of model eval and metrics. And last time we talked about true positives, false negatives, true negatives, false positives, and how those metrics combine into accuracy, precision, and recall. We're going to build on that knowledge, and by the end of this session, we'll get to F1 score and F beta score. Before we jump into that, we're just going to take a moment to look at confusion matrices and further ground our understanding of the true positives, false positives, true negatives, and false negatives as it applies to kind of a binary classification visualization. So we're just going to dive right in. We have about an hour today. So confusion matrix is a table that's often created to describe the performance of your classification model on your test set. And it's substantially useful because it gives a really quick view of how your model is making the decisions that it's making in a way that's very interpretable and easy for another data scientist or statistician to leverage and understand. And again, this is something that you create typically off of your test set or off of your holdout set, as opposed to on the training set that was used to train your model. Here's what this looks like. It bins the categories. It bins the categories of these predictions into true positives, false negatives, and true negatives. Essentially, the green colored boxes are when your model is making correct predictions, and the blue colored, and the blue colored boxes are when your model is making incorrect predictions. So you have your true positives and your true negatives, your correct predictions, and then the blue ones are the situations in which your model is getting it wrong. Hopefully those blue boxes are much smaller numbers than the green boxes. You can see them as I've seen them both ways, as either percentages of the entire data set or actual numbers, or you can represent both within the same box. Okay, this is just a review of the different outcomes that are in those boxes. We talked about this last time, but true positives, again, are the situations where the model is correctly predicting the positive class, and true negatives is when the model is correctly predicting the negative class. So the trues are the situations where the model's right. The falses are the situations where the model's wrong. False positive, you might also hear this referred to as a type 1 error, is when the model incorrectly predicts the positive class, but the actual class is negative. And false negative, on the other hand, is an incorrect prediction of the negative class. Incorrectly predicts that it is, in fact, a negative instance, but it was not. And so that is sometimes referred to as a type 2 error. Okay. I think I pretty much said all the same information, but this is reading the confusion matrix, which maybe we can look at this actual example to read this will be a little more helpful. These are the actual positive instances as you move across the top band here, the true positive and the false negative. And then this is when we made a prediction of a positive instance that was correct, and when we made a prediction across a positive instance that was incorrect. You can, if you take the true positives over these two values in the denominator, you get something called specificity. So based on how you slice this confusion matrix, you can get different metrics. By the way, if you go diagonally, so if you take these correct predictions, true positive and the true negative, and divide it by everything, that's essentially your accuracy performance. So you have sensitivity here, specificity if you go this direction. If you go top down, you get precision. And then if you go top down from this value, you get negative predicted value. So I think that kind of answers one of your questions, which was, does anybody ever calculate the measure relative to negative values? The answer is substantially no. Most people don't care because it's usually the one that there's the signal and the noise. And usually that's more part of the noise that you're trying to ignore and not the signal you're trying to find. However, there is a metric for it. So you can quantify that and you can report that. There's really not a substantial amount of harm to doing so. You can get really crazy with this if you really want to, and you can just keep going. So you're not going to ask you to do anything with this, but it's just awareness for you to know that there are many different ways that you can manipulate the combination of these values to give you different types of metrics and different types of performance. And whether that's valuable to you or not, you have to understand your use case and what you're trying to actually do and detect in terms of whether that would be useful or not. And today we're going to talk a little bit about some use cases in which F1 has been useful, and we'll dive into some examples of when F beta has been useful, and I think that'll enable you guys to kind of navigate that a little more strongly. Okay, so using a confusion matrix, I can't remember if this is an exam question, it may be, but one clever thing you can do with a confusion matrix is you can calculate all of these metrics listed just by presenting a confusion matrix. So I remember one of the times I was most impressed by one of my leaders is I was having a meeting with a relatively senior officer in my organization, and they were kind of versed in the background of data science, and I had presented this matrix to them of my model's prediction and how well it was performing, and they said, that doesn't make any sense. I said, what do you mean it doesn't make any sense? And on the fly, in their head, they were able to calculate the F1 score, the sensitivity, specificity, precision, and it didn't match the number that I had on the previous slide. And I myself was confused because I wasn't sure how that would be the case. And I, took away from that, went back and re-looked at my data, and he was right. I accidentally calculated my matrix off of my training data set, and the value I was reporting was calculated off my test data set. So he was correct that it didn't make sense. And so my just the values I had reported on that to him didn't match up. But to this day, I don't work with this individual anymore, but to this day, I was really impressed by their ability to calculate these metrics just in their head on the fly from that matrix. And that impression stuck with me. So you can, just by looking at those numbers on a matrix, calculate accuracy, precision, recall, specificity, and F1 score. That's something that not necessarily F1 score in your head, but those are some things that you guys should be able to look at, and kind of, if somebody has another performance metric somewhere else, you should be able to sense if that aligns and makes sense relative to that. Okay. I think we have a breakout already. That was very, very fast. So calculate metrics from a confusion matrix. I'm going to drop this in the Slack channel. Did we do this last time already?
No, we did something else.
Okay. I just wanted to make sure I do have these. So this is our...
No, we did accuracy and summation last time.
That's right.
Okay. Let's see, I downloaded implement F beta. Let me make sure I've got the... Oh, I think I missed one. Confusion matrix. Yes, here we are. Sorry, my computer is blocking my download. It thinks I'm trying to download a virus. One moment. There we are. Apparently, my code is very suspicious. Here we are. So go ahead and download that notebook I dropped in the Slack channel. Sorry, I'll have the Google Drive set up for you guys next time. All right, so your goal is to use this calculate metrics function, which takes in a confusion matrix and then calculate the accuracy, precision, recall, and specificity. So I'll share this.
So when we get the formulas all back.
There we are. Yes, I should put the formulas back up on
Okay.
our slide here. I'll pull that old deck up. And so you guys can have accuracy, precision, recall, specificity, or I'll at least drop in the channel too. So try to take in this confusion matrix that's being created and calculate those metrics. I will pull up did I have that in here at all? Here, there we are. We'll leave it on that slide.
Were you down?
What?
Were you able to down? Okay.
I just click the download and I hover over it and download button is there and download is there.
So go ahead and get started on that.
I download and nothing should be in it, but it doesn't care what I do.
It thinks it's like a.
And then like when I hover over it, it's still right. I can see. I get one.
Yeah, sorry. Yeah.
All right, what do you guys have for your breakout session notebook?
Okay, accuracy, I got 98.5%. Precision, I got 90.47%. Recall 95%. And then specificity, 98.9%.
Is that what you guys got? You got too? Perfect.
Maybe we're at my decimals.
Is there like a certain number of sig phase you go to in data science, or is it just like pretty?
We're not physics or anything, so.
Yeah.
I don't know if we even care. We should be consistent realistically though.
We definitely don't use, at least I haven't seen substantial, sorry, I'm trying to figure out how to get back to there we go. Substantial leverage of, well, my input had this many digits, and so my output needs to match the same number of
Yeah.
significant figures. However, from a reporting standpoint and interpretation standpoint, if you report like 2 or more decimal points on your metrics, your stakeholders are sitting there just trying to figure out how to round up in their head to get it to something. So simple, straightforward, easy to read. I would do no decimal points unless there's some meaning in your decimal
Okay.
points, like, and you want to capture that. Small amount of data, maybe 1 decimal point, but I wouldn't go beyond 1 if you're reporting to anybody else other than yourself. You can do whatever you want for yourself. Great. Let's talk about a really cool metric called the F1 score. I think this will just take a second. So the F1 score is, sorry, I have to switch my setup on my computer back to, there we are. The F1 score is a metric that's very commonly used in binary classification, and it's as a fun descriptor for itself, which is the harmonic mean between precision and recall. So this metric takes into account both precision and recall and equally balances them. So as you guys remember, precision is of the things that we predicted to be positive outcomes. How good were we at that prediction? What's the quality of our positive predictions? And as you remember, recall is the ability of the model to capture all instances of true positive instances. So everybody who had the disease, how many of those people did we actually capture? What F1 score is it's 2 times precision times recall over precision plus recall.
Does this mean that F1 score has an inverse relationship with accuracy, like precision does? Or no?
Not an inverse relationship with
Okay.
accuracy, because precision, if you truly are 100% accurate, then you will have 100% F1 score.
Okay.
So they can both be high. Your F1 score and your accuracy can be high. However, you can also have situations where you have a high accuracy and a low F1 score. If you are just really good at the negative classes, you're really good at finding people who don't have fraud, but you're not really good at actually finding people who have fraud or recalling on people who have fraud, then you'll have a low F1 score but high accuracy because of your class imbalance, because there's so many people who don't have fraud. 99.9% of people will cause you to have a high accuracy. But F1 will be 0. In our situation where, remember, we drew out all these instances and we said 99 cases of no fraud, 1 case of fraud, 99.9, and we predicted 0 for everything. Your precision 0, your recall is 0, so your F1 score is 0, but your accuracy is 99.9%. Okay, so this is F1 score, 2 times precision times recall over precision plus recall. What this means, oh, maybe I have another slide that says what this means. I'm trying to, yeah, here, let me just go to the next slide. Getting ahead of myself. So the way that you use the F1 score is it's a harmonic mean between precision and recall, which means it gives it gives equal weighting to both precision and recall. So your F1 score will only be a high F1 score if both your precision and recall are high. If you have high precision but low recall, it's going to weight that appropriately. If you have high recall but low precision, it's going to weight that appropriately. So it's a really tough balance to, it provides a tough threshold to be good at. This value, the F1 score, it scales between 0 and 1. So that formula, 2 times precision times recall over precision plus recall, scales between 0 and 1. And a value of 1 indicates perfect precision and recall. And a value of 0 indicates very poor performance. All right, here is, I wasn't sure when we were going to get to the example here. So here's an example. Let's consider this binary classification problem. Can you calculate the F1 score? What do you have?
93%.
Yes. Look, even you were doing it. You were trying to round that up in your head. Your stakeholders or people you serve your information to try to do the same thing. Exactly. We're able to use those. By the way, what is this, guys? This is a confusion matrix. So you calculated your F1 score from the confusion matrix. So you're able to use those numbers to calculate your precision and your recall. Then 2 times precision times recall over precision plus recall will give you that F1 score. Any questions so far on F1 score? I think this is the last slide before we jump to F beta.
And I think maybe this will be answered after we get that beta and stuff. Is this pretty much just like the one people use? I mean, I know there's been using just, precision or just recall, depending on the use case, but for the most part, is that one pretty?
Rosendo, can you still not hear anything? Sorry. One moment. Okay. Oh, he can. Okay, excellent. Sorry, I just saw your message. I know that was 30 minutes ago. I apologize. I have another slide open on my end here. So great. Is this predominantly the metric that they use was your question, is the F1 score? That was your question, right?
Yes.
Okay. I would say this is a much more favored metric for, especially for classification problems, which is what it's primarily used for. I would say pretty much every data scientist worth their weight understands this metric and knows what it is. There are also a ton of other metrics, and there's a lot of reasons to use those other metrics based on what you're trying to do or what you're trying to accomplish. So it's not necessarily like one size fits all, but it is a fairly generalized and well understood metric, and it's leveraged a lot more than accuracy because accuracy rewards so heavily for true negative predictions. Whereas this one, true negative doesn't come into the picture at all. True negative is not in precision or recall. Man, I should have asked you guys that question. What value is not considered here? It's not in precision or recall, so true negatives actually are not in this formula at all. It weights the other three categories. However, you can, there's a balance, so you can't just be really bad at true negatives and still have a good F1 score, because true negatives are a result of the other three categories combined. I don't know if I answered that very directly. Yes.
With these metrics, does it usually make more sense to leave them as decimal points using percentages? Like, does it make sense to just consider them out a whole? How are they more accurately represented?
How are they more accurately represented versus how I represent them are two different things. I would say representing them as decimal points is probably most true, because this is not a percentage.
Yeah.
This is not 93%. 93% of the data, we're not dividing by the
It's
whole.
not really a percentage. I mean,
It's
like,
not.
you can make it a percentage just between 0 and 1, but it's not really a percentage.
It's not a percentage. However, that doesn't mean anything at times to other people you're reporting these metrics to. So it really depends on your audience that is consuming them, because they're going to make them percentages anyways sometimes, or in their head they're percentages. Sometimes it's easier to read percentages for interpretability. So sometimes people are taking what you're presenting them and mapping that to their domain of knowledge and understanding. So at times, I have been guilty of representing F1 score as a percentage. It's not a percentage, but that's sort of a nuance to practitioners of the field. I would say don't put it as a percentage to other data scientists. You might get called out.
Although an F1 score of 1 does mean your model is 100% correct.
It is
In theory.
It is a measure of performance. It is a measure of correctness relative to a particular slice of the pie. I'm good at indirect answers.
I think you answered the question.
Okay. Any other F1 questions? Those are good questions. I use this metric a ton. Constantly. And the more you use it, the better familiarity you get with what is a good value for F1, because the other commentary I'll add is what a good value feels like for accuracy. Intuitively, we kind of know, 80% is not atrocious. 90% is pretty darn good. 70% is a little yellow. And then you get down to 60%, you're not doing well. F1 has a different feel to it. And so there's one exercise that's really good to do is represent randomness for your own problem. I do this all the time with the models that I build. I just did this weekend. We had a classification model that we were trying to build, and I wanted to know, what does randomness look and feel like for that model? And we had a proportion. Our data set was separated into different proportions. Maybe one class was only 10% of the data set, another class was 8% of the data set, and the rest was this third class. And so I created a simulation that 10% of the time randomly chose this class, 8% of the time randomly chose class 2, and then the other percentage of the time randomly chose class 3. And that was my baseline model for, if we have something that performs worse than that, that's really concerning, because it's worse than random. And as you might expect, the performance across the board for a simulation like that was like 37%, 33%. So a third of the time it was getting each of those classes correct, which, if you think about it, for a 3-class problem, makes sense. So it would be a fun exercise. Maybe I'll put this in your homework assignment. I think I will. For you guys to represent what does random, if you have random for your problem or data set, what does that look and feel like relative to this metric? And we know for accuracy, that's probably going to be 50%. That's what, if you have a model that's performing less than 50%, I don't even know if you could do that, but just invert. At that point, invert your predictions. Well, if it's less than random, just invert your predictions. That means, but
I'm really good at guessing.
yeah. But I think you understand the sentiment, and I am going to add that to my notebook here. Randomness for F1 score. All that was to say, this is a more challenging metric than accuracy to get really, really good at. So that's why it's good to understand. That way you don't have a knee-jerk reaction when you implement this and see a score of, a 0.79 and you're greatly concerned with the performance of your model.
Oh, that sounds pretty accurate.
All right. Anything else on F1? Great. Let's generalize it. So what do you do in a situation where precision and recall, they're not equal? Sometimes one situation is more important than the other, and you want to weight that appropriately in your metric. And that's where you can leverage something called the F-beta score, which it still combines precision and recall. However, it's a generalized formula where in F1, the reason it's called F1 score is because beta is equal to 1. So F1 is the F-beta score. It's just we're setting the beta parameter equal to 1. What if we set the beta parameter equal to something else? Depending on whether we get closer to 2 or whether we get closer to 0, it weights precision or recall. So this is the generalized formula here. It's called F beta, and it's F beta equals 1 plus beta squared times precision times recall all over beta squared times precision plus recall. So in this situation, if you put 1 in for beta, you have 1 plus 1 squared, which is your 2. And then 1 squared is 1 times precision is precision. And that is equals your F1 score, which is 2 times precision times recall over precision plus recall. So that's the F1 score. The F1 score is a particular instance, but it's used so commonly that even packages, there's even an F1 score package, which is funny because there's also a F beta score, which is, it's the same thing. Yeah. So this is the more generalized formula here. All right, let's talk about beta, which is the parameter that you adjust to change. It determines the weight assigned to recall versus precision. And remember that this metric always sums to 1. Oh my gosh. This metric at max will always be 1, and at minimum will always be 0. So if you're giving more weight to precision, that's weight you're taking away from recall. And if you're giving more weight to recall, in order for that to still only be between 0 and 1, that's weight you're taking away from precision. So when beta is equal to 1, that's something called our F1 score, which equally weights them, precision and recall. When you raise it above 1, and the most common value I see for this is 2, theoretically, I think you can put any value in there, but at some point you're just scoring precision, right? And at some point you're just scoring recall. So there's probably some trade-offs there, but the most common value I see for greater than 1 is 2, and that's when the score favors recall over precision. So it makes the metric more sensitive to those false negative predictions, those situations when you really don't want to miss something. You want to capture every single thing, even if when you capture those things, you're a little more imprecise. When beta is less than 1, we favor precision over recall. And that means that you're only rewarded for making really accurate positive predictions. When you say something happened, gosh darn it, it really did happen. So that makes it more sensitive to false positives. I want to give examples. Okay, I'm just trying to decide the right spot. I think I'll give an example here. Let me look just a little further in the slides. Yeah, I think I'll bake in the example here. So a situation when I've actually leveraged this in real life for work is when a previous company I've worked at before, they had a bunch of contract documents and people could make comments on this contract document. I think I've told you guys this one before, but now you can map that relative to this score. There were about 9 teams that had to take an action on that document based on the comment that was made. One of those 9 teams, or 2 of those 9 teams, or 3. So N of those 9 teams could take action on that document. So we had a document, and we had some comments. A comment, and now the question was, does this person need to take action? Does team, I got scared for a second. Team 1 need to take action 2. Let's just, let's say 4. We're not gonna do 9, that's just too much. And the question was action, yes or no, action, yes or no. Action, yes or no. Action, yes or no. And one thing we could do is if we balance precision and recall, then we're balancing the number of times we over-notify somebody versus the times that we under-notify somebody. So over-notify, you tell them you're annoying, it's too many notifications because they didn't actually need to take action. Under-notify is, ooh, they should have done something with this and you didn't tell them. And so the business said, over-notify us, please. Like tell us too many times that we need to take action on this document. We would rather open this, look at it, and then close it and be like, I didn't need to do anything, than miss something and have that go by. So in that case, we highly weighted recall. We wanted to catch every single instance. Our model wasn't really precise, but it had a really high, we weighted that with the F beta parameter. So which of those scores would you do if you wanted to favor recall?
It's entirely or slightly more.
Would it be
Go.
base greater than 1 or beta greater than 1?
1.5.
Because recall has false negatives.
Yep. So we did a F score of F2. So you can actually, just like we call the when beta equals 1, F1, you can call your metric F2. We used an F2 score. So you don't, once you choose your beta, you don't have to say I used an F beta score. You just use the actual numerical value you assign to that. So that's exactly what we did. We used an F2 score. While I have this on the whiteboard, a really interesting piece of this that I want to tell you guys is there is something different between a multi-class problem and a multi-label. So multi-class is when you're predicting, is it a cat, is it a dog, or is it a banana? You can't be a dog and a banana. You can't be a dog and a cat. Banana dog. This is an or statement. So this is multi-class. These things are exclusive. And the way that we model that is a sum of probabilities that sum to 1. So when you have a set of probabilities, 0.1, there's a 10% probability you're a cat, When you have output from your model, it'll be like 0.8, there's an 80% probability that you're a dog, and there's a 1 probability that you are a banana. 0.1, because they have to sum to 1. So if we, this has to sum to 1. Always. All of your outcomes must sum to 1 in a multi-class problem of all the probabilities of the different classes that you could be. This is not a multi-class problem. This is a multi-label problem.
Is it technically binary, so it's yes or no?
It's technically binary because it's yes or no. So what basically both of these are is, remember our logistic regression sigmoid function? This is its own logistic regression. This is its own logistic regression. This is its own logistic regression. Or if you want to think about this in neural network terms, this is a sigmoid activation function as an output layer. So we've got, here's our input layer, right? This is extra content for you guys. This was not in the slide, sorry. This came up recently. I thought it was an interesting thing. And so if this was a multi-class problem, we would have one output neuron that output the different probabilities associated with our classes, and we would use a softmax transformation, a softmax, to make those probabilities sum to 1. In a multi-label paradigm, these probabilities, these do not sum to 1. 2 things. 1, these do not sum to 1. And each of these actually has 2 probabilities associated with it. What are the 2 probabilities?
Probability of yes and probability of no.
Probability of yes and probability of no. Realistically, we just report 1 because you can calculate the other, these will sum to 1. So 0.1, 0.9, 0.2, 0.8, which usually you'll just report the probability of yes. So maybe that's 0.1 here, 0.2 here, 0.7 here, 0.6 here. So now you have all these different probabilities. How do you choose which people need to take action? Let's say this is legal, this is sales, this is HR, and this is what?
Accounting.
Accounting. Thank you. Thank you. I was struggling, and if you couldn't tell, departments. Who needs to take action on this comment based on these probabilities? 0.1, 0.2, 0.7, 0.6.
Side is yes and side is no.
Oh, I'm sorry.
I'm like,
This is
whatever side's yes, but like I don't know which side's yes.
I'm sorry. This is the probability of yes.
Okay, so
Probably
I'd say
sales.
sales and legal, yeah,
How'd you guys know that?
because they had a high probability of yes. Higher than 0.5, which is
Use
usually the
threshold.
standard
Yeah.
boundary.
There we go. You got it. You nailed it. All right, you guys hit all this. You all definitely have passed the previous class, I can tell. So we set a threshold value for each of these. And one thing you can do, this is coming full circle now, I promise. When you set your threshold value is you can balance how many true positives do you want, how many false positives do you want. You can balance your precision and your recall with that. So one performance metric you can use to help reward your model properly based on that is your beta score. So F2 score applied to these weights recall over precision. So we over notify, so we'll probably notify. So the difference with this one, by the way, multi-label compared to multi-class, is you can be both sales and legal. Both of these situations can be yes. You can have multiple labels where the answer is yes. Whereas in multi-class, you can be a dog and a cat. It's exclusive events.
Do you have only one model for each department, or do you have like one model, or do you have one model that handles all 4 departments, but like they have different paths they go on based off, okay, you fulfill this condition, you have that condition, we do another condition, oh, it's this, or would you make them separate out so like they're not conflicting with each other?
You can do either situation.
Okay.
I've definitely seen it done both ways. In this one where the reason I drew the neural network is, which I did the softmax layer and then I didn't show you the layer. The other way that you would do this is you would just have, instead of softmax, you would do an output of 4 nodes, and this would be a sigmoid transformation.
Okay.
Right, a sigmoid activation function. Right, 4 of those though, 1 for each of your class. And that structure, it's the same model.
Yeah.
It's the same weights and biases, maybe that's a better way to put it, same weights and biases, different outputs. Or one output represented as independent probabilities. These are representing these as independent events. Okay. Cool, that was a little rabbit hole. Oh no, my screen. I talked so long that my computer went to sleep. Let me make sure we didn't lose StreamYard. Oh, yep, we did. Okay.
Oh no.
Yeah, 1 moment. I'm still connected, but I have to share window. All right. Let me see where we're at in the slides, how many more we have here. We have a couple and then we're at the breakout. And so I won't take a break now because we only have just a few slides left. All right, how do we interpret this value? As we talk through metrics, I'll let you guys know if this is a metric you should maximize, if this is a metric you should minimize, because it does change. You're not always trying to go towards 1. In this case, we are. So in this situation, the score ranges from 0 to 1. You'll never have and that's not the case with all metrics we use. Some of them go beyond 1 or less than 1. So, but for F beta, 0 to 1, and we're trying to maximize it. So a score of 1 indicates a better score. All right, let's look through an example. Calculate the F2 score here. You've got a precision of 0.75 and a recall of 0.8. All right, what'd you guys get?
0.94.
Is that what you got?
My 789.
Oh no, there's contention, and you know
It
what?
could be,
I really, I'll be honest, I'm not
No,
guaranteeing
sorry.
any of mine.
I don't
it
have
was
a.
probably where I was trying to cheat.
Oh, I do have an answer slide.
I'm not guaranteeing this.
What was yours?
Wrong, because I used
981?
the precision recall from the last example.
Oh, okay.
0.789,
All right.
that's what I have at least.
Yes.
I-
Okay.
So-
I was like, I never know.
That was
It's
that
like,
far off.
I have enough parentheses that if I drop one, it will break it.
No, that must have been quarter buck, right?
I goofed up my slide order here, so for some reason I have F beta summary and then the answer to the example. I think I reordered some things on accident, so I'll go to the summary right after this. But yes, here you are.
Okay.
So do not leverage your previous precision and recall. How dare I make the slides easy enough for you to do that? No, I should though. Yeah, 789. So common values for beta include 0.5, 1, 2. I've also seen 1.5. You mentioned that. I've seen that as well. I've not seen anything greater or below those values. So I don't know if that's, I'll have to play with that and see if that does a substantial change that makes it not meaningful. But F1 score is definitely the most common variant. Like I said, it even has its own function, which is kind of funny to me. And it's the most balanced metric. So you guys are just gonna have to decide for your use case, do you wanna over notify? Do you want to under notify for some reason and only do it when you're really, really, really certain?
Do most people just test each of the beta values within their pipeline and determine if that has like a positive impact on their scoring? Or do they actually think beforehand about like, is this the type of data that I need?
Usually the beta metric is the performance standard that you're setting for your model so that it can learn its weights and parameters to best get that outcome. So you're basically telling it, how do I win at the game?
Yeah.
Here's my problem. And if you did really, really well at the game, how do you know you won? And so it's something that you would define before you trained your model. But the model that performs best on it is hopefully you align it to your outcomes for your problem so that the model that performs best actually accomplishes the outcomes that you want. So probably one of the most important exercises you will ever do in machine learning is actually understanding what your success criteria is, what your success metric is, and how it aligns to the business problem you're trying to solve. That's why I'm so passionate about not using accuracy for everything, because I just think it's grossly overrepresented, and I see it too many times. And it's not really aligned with the business objective or outcome for that problem. All right, let's implement this. Build your own F beta, guys. I will drop in the Slack channel this notebook. Additionally, opening it on my own computer here so we can, forgive me while I move my screens around here.
It's still.
This one came in.
Oh,
It
okay.
came in like an actual download.
Weird.
I do have an update from ChatGPT. You can use Colab to download your folder and then like copy it to your folder for your drive.
Oh, I'm gonna do that.
Like there's.
I'm gonna do that
It's like
'cause
3 full lines together.
Send those to me. Thank you. I'm gonna do that because I didn't want to go through the manual effort or give a bunch of permission to a tool that I know nothing about. So that's substantially useful. That's exactly what I said I wanted when I said, yeah. That's perfect.
That's how you mount it. And then you do the thing.
I will do that. And that's going to be much better than trying to. Then you guys will have access to all of these in a way that's appropriate. Here we are. F beta. So when F beta, when beta is equal to 1, then F beta becomes the F1 score, which is the harmonic mean between precision and recall. So this is the F1 score here. And what I would like you guys to do, so in this function example, we create an F beta score. Oh, sorry. That given precision and recall and a beta value returns the F beta score. So your goal is to implement a F beta score. And I'll scroll back to the formula on this slide. And I gave you the way to calculate F1 score as well already, so you can kind of just generalize that. Here is F beta.
Does anyone know if I can use Caret in Python?
That's double star, I think.
No, definitely.
For to the power of, or for what?
Yeah.
For squaring. I don't.
Double star.
Is it double star?
Double star.
I think even in Java, I have to do the math one.
The one that has taken me the longest to break myself of is, I lost it. It's gonna, I'll let you know.
We'll never
Come
know.
back as soon as you leave class.
Right, it'll.
I was really impressed.
Not equals.
Oh, does not
I was
equal.
always used to this.
Oh, for
Really?
SQL world?
Yeah.
Yeah.
No, I started off with exclamation point equal.
That's
what I
because you
default
came
to.
from the programming world of Java or something to that effect.
I came from the humble beginnings of Excel.
Mhm.
Since I started with Java, what drives me insane about Python is that they write out the ors and ands instead of using like the double ampersand or the double bars.
So much more
I'm just like, why don't you just write it out? Like, it's so weird.
By the way, I had to dive into some deep SQL this weekend for the first time in a little while, in a hot minute, and I was wildly impressed with the built-in capabilities of the language model that's in our platform. It's in Databricks, the Databricks Assistant. I gave it very complicated logic in human language, and then it wrote multi-line SQL queries that were, I mean, I had to tweak them from here and there,
Yeah.
but generally the output structure was pretty good and was way faster than me trying to recall from the cobweb depths of my memory how to do that exact thing. I was really impressed.
Wow.
All right, what do you guys have?
I mean, they tell you what you're supposed to have.
Oh, yeah, I guess I do. Did you guys get it correct?
Yes.
Nice. And that wasn't too unfriendly. How do you feel about F beta, F1 score now? Was it something you guys were familiar with before?
I definitely did F1 score. I don't remember F1 beta that much. I haven't dived into it very much.
Taught you something new. All right, since it's a short day, we're just gonna keep going to touch on log loss, but I'll probably touch on this again when we meet next time, which we also talked about this a little bit in our discussion session last time. So this will probably be 3 times of you hearing this by now. It is an important metric. Oh my gosh, you should not eat chips and give me 2 seconds. It is an important metric. So if there is one thing that you take away from this class for binary classification, please let it be F beta score. Because if you're going to go to the work to look at F1, you might as well do F beta. If there is one thing for regression output, let it be log loss. And actually, log loss can apply to. Are we talking about this? Yeah, actually, we're talking about this in terms of binary probabilities. I'm changing my mind. Forget F1 score. Focus on log loss. It is an important metric because this is substantially what's used in the realm of neural networks, and I just think it's a really fabulous metric, and it comes from common sense and common knowledge. Like I think Skylar, like pseudocode developed this just riffing off thought process in our last session. So it's very intuitive, and the formula looks a little hairy when you first look at it, but when we break it down, I think it'll resonate with you guys. So log loss, otherwise referred to as logarithmic loss, sorry, just gonna open up my other slides on my other screen here, is, or cross entropy loss. You'll sometimes hear that as well. It's an evaluation metric used to assess the performance of binary classification, not to be confused with what I just confused in my head, which was our, I was confusing it with like mean squared error, root mean squared error, but logarithmic loss is the performance for binary classification leveraging the probabilities actually predicted by the model compared to the labeled outcomes. So prior to this, we have not talked about probabilities at all in any of our performance metric. Accuracy, precision, recall, F1 don't care about your probabilities. They sort of do in that you can adjust your threshold to change how you apply your labels are, but they are not actually using directly the probabilities generated by your model. This one does. And let me just move to the next slide, or I'll say everything on one slide and I have nothing to say on the next slides when I go to it. Okay, here is the mathematical formula for log loss. It is the negative. We have to take a negative value because in the equation there are negative values that get calculated, so we have to negate that. And then it's 1 over n. What is 1 over n doing? It's just averaging. So we're going to do this for all of our outcomes. We're going to run this formula. That's the I to n for all of our outcomes. The 1 over n is just saying, on average, what's the performance? You'll notice a pattern that pretty much all performance metrics do that. They just average across all these. So in this formula, there are two parts of we have y at I log p of I plus 1 minus y at I log 1 minus p of I, which looks intimidating initially, but I'm going to switch to the whiteboard here. Well, let me see what our next slides are. Yeah, I think now is a good time to whiteboard, and I'm going to do the same thing that we did last time, but not on the record. Oh, I have to erase all of this. Give me one moment. You guys good on this? Okay. All right. So the log loss formula, I want you to think of the log loss formula in two parts. I want you to think of it as the scenario when the predicted, the scenario when the outcome is 1, or when the ground truth label is 1, and the scenario when the ground truth label is 0. Okay. Are we doing on time? But yeah, we got time. Okay. Let's do loss is equal to negative 1 over n. And then the sum, the sum from 1 to n of y at I. Well, that's some sort of bracket, should be a round bracket, sorry. Y, I'm just gonna do y. I'm gonna drop my i's. Log p, you guys know that we do this for each instance, plus 1 minus y log 1 minus p. Okay. Close this. There we are. So here's our formula. For now, we're gonna drop 1 over n, and we're gonna drop the summation function. You guys know that we calculate this for each instance. So you know that if we have, let's say these are our probabilities and outcomes. Actually, let's say here's our y pred. And let's do our y true. Here's our y pred, let's say 0.8, 0.2, 0.7, 0.3. Sorry, I was getting my commas in. Comma. comma, decimal. Sorry, a little mixed up there. Okay, and let's say our y true is here where we're wrong, we were correct, and we were wrong. Let's make this an A, sorry. Okay, no, I already have that example. No, I was right, 0.3, we were wrong, I was doing it. Let's do that. Okay, so in this scenario, we predicted 0.8, which would have turned, assume a threshold of 0.5, that would have turned into a 1. 1 is not 0, so in this instance, we were wrong. 1 compared to 0.2, 0.2 would have turned into a 0 if we were using thresholds. So in this instance, we were wrong. 0.7 would have turned into a 1. In this instance, we were correct. And 0.3 would have turned into a 0. So in this instance, we were also wrong. Makes sense? Okay. So you guys know, back to what I was trying to say before, you know that we are going to calculate the log loss. Just do it over here. I'm trying to figure out how to represent. You know we're going to calculate the loss for this instance, plus the loss for this instance, plus the loss for this one. I should don't think I even need to say this, but then you know we're going to divide those by 4, right? To get our loss. Okay, so because you already know that, I'm just going to drop this initial part of the equation, and let's just focus on this middle section here. So let's focus on y log of p plus 1 minus y log of 1 minus p. Okay? I can even drop my parentheses here. I'm just trying to simplify this equation for you. So I want you guys to think about this equation in 2 parts. I want you to think about it in this first half and this second half. And that is because at any point in time, only one of these situations will be 0. The other will be a metric. And in the other situation, one will be 0 and the other will be metric. So let's look at this. When y true is equal to 0. So when y true is equal to 0, that means we have 0 times log of p, which is equal to 0. So essentially we have 0 plus this half of the equation, which is just this half of the equation. So when y true is equal to 0, that's this one. I'm going to change colors. When y true is equal to 0. Should I put a double equal sign up here? Equals to 0. It's not an assignment operator after all. So if that's the case, then this must be active when y true is equal to 1. So let's look at that. So when y true is equal to 1, what happens in this equation? This part of the equation.
That one goes away.
This one goes away. So we have 1 minus 1, which is equal to 0. 0 times, well, anything is 0. So this equation is gone. So when y true is 1, we're only taking this one. Okay, so let's further break this down. So when y true is 1, this is just 1 times log of p. So that means essentially when y true is equal to 1, we're just taking the log of the probability. All right, so when y true is equal to 0, a similar situation occurs here. We're taking 1 minus 0, which is 1, and we're taking 1 times this equation. So we're just looking at log of 1 minus probability. So you're either taking the log of p or the log of 1 minus p. And the reason, does anybody know why we're doing that? Why wouldn't we just always take the log of p?
is based on the values, which one you want to show that there's more distance with. So like with 1, you're trying to show, hey, as you get closer to 1, it's more accurate, and so you get a smaller value. Or, yeah, I think smaller value, 'cause you want a smaller difference.
That's exactly correct. So if we predicted 0.8, for example, if the ground truth label was 1, like you were saying, well, then we're doing pretty good, right? We're only 0.2 away. Good job. But if we predicted 0.8 and the label was 0, we're not doing very, very hot. We're 0.8 away. That's not very good. So we want to punish that. And because even though the probability was the same, we need to measure the distance to the true label. And that's what we're doing with that on-off switch and the P and 1 minus P in those various situations.
I have a qualm.
Ooh.
So last time when we talked about this in brief, I was thinking about the formula. I was thinking about log loss, as we all do.
Yeah.
On the way home.
As we all do. Regular occasion.
And I think they overcomplicated it. It's clever,
It's clever.
but why don't you just do your y minus your predicted absoluted with log over it? It's
Okay,
the
hold on.
same, it's the same thing except less complicated.
Absoluted with what?
So the y true minus
Yep.
the predicted
Let's try it.
absolute, and then you log over that.
That's predicted, absoluted, and then log this. This?
Yeah.
All right, let's try it out. I'm a big fan of this. First of all, we need a use case to work with. So let's use case, oh gosh, too many word words. We need an example. So log of P, let's just do these, I want a correct example and a wrong example. I hate that there's not a third color here. It really bothers me.
There's that blue marker over there.
Oh, no, that one almost got me last time. Nobody wants this indefinitely up here. Okay, really bothers me because I want that to be blue. But, all right, let's do a situation where it's wrong and a situation where it is correct. And so let's do 0.80. So in that case, our y true is 0. So we get log of 1 minus p, which is the log of 0.2, right? Okay, so this is what we get for that situation. That was our incorrect situation. Let's do our correct situation. Sorry, did I do, that seems wrong. Did I do that correctly? When it's 0. What's the log of 0.2?
Wait.
This should
The
be,
y is equal to 0. Oh, yeah, actually.
Is negative 0.698.
Wait, are you doing the log or natural log?
do the natural log. I had this come up as a
I don't
question
know,
last
this
time.
is
Try the
what
natural log.
Excel wants me to do.
Negative 1.61. I think that makes sense, because you were
Okay.
expecting a 0 and you got.
What is the natural log of 0.8? I just want to make sure I'm telling you this correctly.
Natural log of 0.8 is negative 0.22.
We're good. Okay. So this is a higher loss value. So there's
Yeah.
higher loss. So that's bad. That's worse. Okay. I just want to make sure we're on the right track here. So let's do this one. When it's 1, we're taking the log of P, which is the log of 0.7.
Negative 0.356.
Perfect. So this is a better loss value than this one. I'll take the negatives off because that
They
gets
don't really matter.
they get negated here. So so that's a better loss value. This is smaller than that. So let's try it here. Y true. You said Y true. So let's try it for this one. It's 0 minus 0.8. This would actually be in that situation Our negative situation would be a log of negative, so y true is 0 minus 8 plus, so that turns into a positive, so log of 0.8, which gives us,
Didn't we do that? Oh, no, we didn't.
we did, no, we did, it was
We said
No,
things
no,
are
no.
the opposite.
Because we're trying to flip it.
Negative 0.223.
All right, let's try it in the other situation, 1 and 7. Y true is 1 minus 0.7 is actually 0.3. So in our good situation, we're taking the log of 0.3. So this seems inverted to me.
Got it. Well, then we just do 1 minus.
Yeah, but it also doesn't have the same proportion, so I don't know how well it'll hold in comparison.
So this would be 1 minus the absolute value of y true
There we go.
minus predicted. So in that case, this was
Because that would give
0.8
us
and then
those.
0.2, and then this would be
0.7.
0.7.
I will
See,
say
it feels cleaner.
I will say mathematically, absolute values is more difficult to handle than a summation and the one.
Okay, so computationally.
I feel like it's easier for them than absolute value, because that's like a whole different function.
This is interesting though.
And that's the same. in
I would
theory.
probably agree, this probably leans a little better towards matrix algebra, which is what we get to in neural networks. So if it's from a computational perspective, I don't know, but it might be harder to apply it. I'm taking your word on that one.
I
I'm
feel
not
like it's
sure.
more difficult to deal with absolute value in your program without like an absolute value function.
Yeah, there probably is. So how are you guys feeling about this formula, by the way? Because I want to check time here. Feeling pretty good? Cool. We may not need to go over this again next time. Let me switch back to slides here. And we've got 3 minutes, so I'll just go through the last, outcomes here. And that is, I meant to say this when I had that board up, but the thing to take away with log loss, I think you can see based on this, it penalizes confidently wrong predictions. So if you confidently say 0.9 probability, 0.8 probability that this is of class 1 and it ends up being class 0, that's a much heavier penalty than if you said, well, I'm conservative. So what this metric tends to do is create conservative models that only really say something's going to happen if it's pretty sure about it, because there's a heavy penalty for bluster for models that just say, yep, I'm very, very certain that this is the case. I think that's my favorite thing about this metric. Confidently wrong, penalizes confidently wrong predictions. Okay. So in the interpretation, the way to interpret this metric is that a lower loss is better. This is not the same as accuracy, precision, recall, F1 score, where we're trying to maximize to 1. This one, we're trying to minimize this. We're trying to get as close to 0 as we can. So if you have a loss of 0, that represents like a perfect no loss. You were 100% correct in your predictions. So you're trying to get to 0. It can go beyond 1 as well. As we saw in this example, right? We had, if there was only one value here, this was 1.61. So you can have a loss. You shouldn't, I'd be scared if you did, but you shouldn't, you can theoretically have a loss that's greater than 1. If you do, you should look at inverting your predictions, but but you theoretically can. So it's commonly used as an evaluation metric for binary classification problems when you have model probability outputs. Now, not all algorithms produce probability outputs. What's an algorithm you guys know of that we talked about in the last class that doesn't produce probability outputs? It's exactly the one I was thinking of. I mean, theoretically, you could count the number of, you could, but it's not a probability. So there's no probabilistic outcome. I wouldn't use log loss on k-means clustering. So You can only use this with things that actually output model probabilities. Do not feed your transformed model outcomes. Make sure you always feed the probabilities to this metric or you'll get weird values. All right, what's the log loss here? Oh, what's the log loss of the first one? Sorry.
Oh.
No, did I do
I
all
think
of
it's
them?
all of them. This is what it sounds.
No, yeah, calculate all of them actually. I'm trying to look at my answer slides here. Oh yeah, no, it's all of them.
I do not know if I trust my math on this one.
I don't know either, but
What'd you guys get?
0.977.
No, but I don't know if I trust my math on this one.
No, no.
Oh, nope. There we are.
Mine was not right either.
So these are the losses at the top of the individual ones, and then this is what I had for the total loss. And then divided by 5.
I have no idea.
There could be an error in here too, so I don't trust my math either.
If I individually did them, I'd be able to check better, but I'm not individually doing
Maybe
these.
the second one did not get that, but I could be wrong.
Let's look at the second one. I have the calculations for each of those written down. Hold on. Just cleaning up the whiteboard here.
Second one.
You're looking at confidence, divide by 5.
Here's the second one, 0 times the log of 0.3. So basically it's 1 times, it's the log of 0.7. Yeah,
It should be 0.35667.
natural log or regular log?
Natural log.
I think I have an error on my slides, so you are correct.
Oh, so I'm wrong.
I think it's actually the natural log, but I will confirm. I believe somebody asked that question last time, and that, if I remember correctly, that was my finding that people say log because nobody wants to say natural log every time.
All together,
Yeah,
0.977.
yeah, I have that one, I changed it now.
Okay, that's correct. This slide is incorrect. You guys, it was a trick question. I was actually checking to see if you guys were paying attention. No, that's fantastic. Thank you guys. This is it for this session today. And next time we'll move on to the next section of content. So we'll see you guys Wednesday.